Here we present our work, Timestamp Supervised Action Segmentation with Graph Convolutional Networks, and the speaker is Hamza Khan. This is a joint work with Sanjay Harish, Uwais Ahmed, Shakib Siddiqui, Andre Konan, Dr. Zishan Zia, and Dr. Kwok Hui Tran. Human activity video datasets can provide valuable insights for guiding, monitoring, and standardizing the activities being performed. However, we are often required to deal with untrimmed videos containing a complex activity. Here we tackle the problem of temporal activity segmentation where, given an input video capturing a complex activity, the task is to assign each frame of the video to one of the action or sub-activity classes. However, training deep neural networks for fully supervised action segmentation requires costly frame-wise labels. Our approach alleviates this problem by using timestamps, that is, labeling a single frame from each action segment. As reported in Fanma et al., annotators need 6 times longer to annotate the start and end frame compared to annotating a single timestamp. To our knowledge, one of the earlier works to investigate timestamp supervision in the context of video recognition was published by Moltisanti et al., in which they replaced expensive action bounds with sampling distributions initialized from timestamps located around each action instance in untrimmed videos. And more recently, Lee et al. Proposed an approach to train a segmentation model using only timestamps. In contrast to Lee et al., we trained the segmentation model on dense frame-wise labels learned by the GCN using timestamps rather than generating these dense frame-wise labels using heuristics. Our approach is divided into two stages, the initialization stage and the refinement stage. First, we'll look at the initialization stage. We start off with a video that is passed to a segmentation model. In our case, we use MSTCN as a segmentation model. Our segmentation model is then trained for 30 epochs by using the sparse timestamps as ground truth. The initialization stage helps us to generate better frame-wise features than the same segmentation model with random initialization. After the initialization stage, we move to the refinement stage. Here, we aim to use the frame-wise features learned by the last layer of the segmentation model during the initialization stage as input to the GCN. For each video, we construct a weighted graph for the GCN. Within each graph, all frames along with their features are considered nodes. Finally, we assume a temporal window within which we connect all neighboring nodes with weighted edges. We define the edge weights between nodes as the cosine similarity of their corresponding features. We then train the GCN on sparse timestamp labels and predict on all frames to get dense frame-wise labels. After generating these dense frame-wise labels, we then switch to our segmentation model. This time, we use the dense frame-wise features that were learned by the GCN as the supervision signals to the segmentation model. This completes a single iteration of the refinement stage, and we perform 20 iterations to refine both the segmentation model and the graph convolutional network. We first conduct some ablation study experiments to understand the impact of graph structures on our approach. We evaluate the performance of our method using different types of graphs, that is, binary graphs and weighted graphs, as well as various temporal window sizes. We can observe from the results, temporal window size of 3 performs worst, while larger temporal window sizes, which are able to capture longer range dependencies despite having higher computational costs, often yield better results. Next, we see results for label generation using GCN and an MLP. As we can conclude, GCN outperforms MLP across all metrics on both datasets, which confirms the advantage of using GCN over MLP for label generation. It is important to note that they have the same set of hyperparameters. Here we conduct experiments to support our choice of alternating learning over joint learning of the segmentation model and the graph convolutional network. It is evident from the results that alternating learning outperforms both joint learning and naive learning by large margins. The bad performance of joint learning is likely because as we train both models from scratch, during the first few iterations, the features extracted by the segmentation model and hence frame-wise features predicted by the graph convolutional network are not meaningful. We now compare the performance of our approach against that of the state-of-the-art timestamp supervised method on the 50 Salis dataset. In addition, we include results of fully supervised methods and transcript supervised methods. Our approach outperforms action boundary estimation on F1 scores and edit distance while performing on par with ABE on accuracy. Next, we present the results of timestamp supervised methods and fully supervised methods on the GTEA dataset. Similar to the results on 50 salads, our approach achieves higher F1 scores and edit distance and lower accuracy than ABE. This shows that our method is less likely to suffer from over-segmentation. Moving on to the breakfast dataset, we see the results of methods with different forms of supervision, including full supervision, timestamp supervision, transcript supervision, and set supervision. Our approach, similar to ABE, obtains higher F1 scores and lower edit distance and accuracy. Next, we present the results for the desktop assembly dataset. From the results, our approach outperforms ABE on F1 scores and accuracy by substantial margins, while performing on par with ABE on edit distance. To conclude, we propose a novel method for timestamp supervised activity segmentation which utilizes a graph convolutional network for generating dense, frame-wise labels from sparse timestamp labels. The graph convolutional network is learned in an end-to-end fashion to use not only frame features but also connections between neighboring frames. Moreover, we present a framework for alternating learning of both the segmentation model and the graph convolutional model. We also show that our method is superior to other weakly supervised approaches while performing on par with or better than the state of the art in timestamp supervised activity segmentation.